Yeah, so thanks, and thanks first the organizer Muxin and Zhang and also all the local organizers to have this very nice school. And I'm be happy to be here to present something about the spin-form numerics. So you see this is exactly for EPR model and related extended EPR models. And we will show how to calculate the amplitude and the observables related to the model. So we'll go to really a very special formulation. So actually, for EPR model, we also have a different representations. It's the same model, it's just a different representation. And this numerical method are associated to these different representations. I should say this is the representation instead of formulation, but it's the same model. So for the small spin regime, we have the booster decomposition, which we can decompose the model as a 15G symbol. I'll tell you later what it is, plus some booster functions. And this makes it possible to calculate the amplitude exactly for the small spin, which is the deep quantum regime, as Francesca already told you. And then for the large spin scheme, which also connected to the semi-classical and the classical probability series, is the integral formulation, which these two approaches are somehow related to the coherent state or the coherent intertwiners. And for the integral formulation, we have the asymptotic expansion, and we can talk about the real and also complex critical points. And also we have the Lipschitz symbol method, which somehow in between in the intermediate regime, which is no perturbative, but it's also very hard to calculate for very small spins. So I hope I'll cover both methods. And so for the first two lectures, I will introduce some basic stuff for the, so basically all the spin form, the special spin form representations, and the basic Lipschitz symbol methods. And in the third lecture, I hope I'll give you some concrete examples how to do the calculation using numerical package we already have, and with very simple examples. For the first two lectures, it may be a little bit technical, so we start with the introduction to the EPR model and its extension. So we start with triangulation, which is the graph it's based on, and then we introduce the transition amplitude, the form of the transition amplitude, and we also introduce the booster function decomposition, and finally the integral representation. I'll give you basically all the stuff. It will be a bit technical, but in principle, if you follow, I mean, you don't need to follow it exactly during the lecture, but if you have time, you sit down, you are able to calculate all the things for what I give it to you. So I'll send the slides to you later on, and then all the formulas are in principle, all the formulas are there, and you can do the calculation yourself. You will get all the results. And then I'll give you an introduction to the saddle points, basically the solution of the equation motion, and what is the Lipschitz symbol method, and how we use it to calculate no perturbatively the path integral. And finally, we have the numerical examples. Okay. So feel free to interrupt me if you have any questions. So let's first start with triangulation. So we are focused on 4D because we live in a 4D space-time. So the triangulation is given by something we call four simplex. So what is the four simplex? Is the generalization of the triangles. Our tetrahedron's triangle is 2D triangulation. Tetrahedron is 3D triangulation. So four simplex is the 4D triangulation. So we know triangle is given by is a convex hull of 3 points. It's a triangle. Tetrahedron is convex hull of 4 points. That's tetrahedron. So four simplex is a 4D polytope as a convex hull of 5 points. So 5 points gives you the four simplex, and it's in this graph where we have you can form it as 5 points, and each 4 points will give you a tetrahedron. So it's here. So in total, we have 5 tetrahedron, which we call it E. I'll tell you later why we call it E. And then for each 3 set of points, we have a triangle. That's the boundary of the tetrahedron. So in total, we have 10 triangles. You can simply calculate. It's like 5 multiply 4 multiply 3 over 3 multiply 2. That's 10. And then each 2 points gives you a segments. So in total, we also have 10 segments. That's the basic geometric objects we can have for the 4 simplex. Of course, finally, we have 5 points. One more thing is, okay, 4 simplex is described by 5 points on space-time. Of course, modular transformations, Poincare-like transformations. But it can also be described by 5 normals. And these 5 normals are subject to something called the Minkowski theorem, which is the closure condition. It says that the 5 normals multiply the volume of the tetrahedron, summing over gives you 0. This is the closure. It's also the same thing for the triangles. If you have 3 normals of the triangle with the edge lengths of the triangle, the summing over it gives you 0. It also can be described by 10 bivectors, which corresponding to the description of the 10 triangles, or 10 lengths, which is the description of the 10 segments. So why we call it bivector is if we have a triangle in 4D space-time, if we want to determine this triangle, we need 2 normals instead of 1. In 3D, 1 normal defines a triangle or a surface. But in 4D, to define a surface, we need 2 normals. So that's the bivector. And the bivector is defined as a wedge of 2 normals and multiply the area, where this is the area of the triangle. So equivalently, a 4 simplex is either given by 5 points, 5 normals, 10 bivectors, or 10 segments. These are equivalent description. I mean, you can do some easy exercise. Given 5 points, you can derive all these kind of numerics description of the 4 simplex. If we have time, in the 3rd lecture, I'll show you a concrete example. So, but this is the triangulation. So, as you already know, the spin form is defined on a door graph of the triangulation. So what is the door graph? The door graph is going by the following. So the 4 simplex is connected to a vertex V is the center of the 4 simplex. You can understand something like this, but it's abstract object. And all the boundary, the 4 simplex contains 5 tetrahedron, and these 5 tetrahedron are given by 5 edges. So edges corresponding to the tetrahedron. So we call these 5 edges E1 to E5. That's why I call the tetrahedron also with E. So you can call tetrahedron E1 to E5 because each edge is dual to a tetrahedron. And then we have 10 triangles. This is given by 10 faces. What is faces? Faces is the thing that between 2 edges. So this is the face, if you want. So we have 5 edges, and they span 10 faces. So these are the door objects. So, and usually it's called a 2 complex because it's given by vertex, edges, and faces. And spin form is built on this 2 complex graph. So this is a single vertex graph. Of course, it only corresponds to a triangulation simplex. We have another graph, which is the boundary graph. Because I think Francesca already told you that for the boundary, the spin form model the boundary is given by the spin network states. And the boundary graph is exactly we cut the 2 complex graph with boundaries. So each edge, we cut it with a node, and each face is cutted by link. So here is the cut, if you want. And if you write out the cut, it gives you this very nice, again, very nice diagram. You will always see this kind of diagram. And this is the boundary graph. Are there any questions? No? Let's continue. OK. And this boundary graph, again, given by boundary nodes, we call it N, is corresponding to the tetrahedron. And we have faces here, now it's corresponding to links. So we have 10 links and 5 nodes. And this now is, so in the spin form model, this boundary is given by the boundary spin network states. So if you things, so Christina already told you some basics about spin networks, you know. So it's actually a 4-valent spin network. So each node, they have 4 valence. And we know if we color each link with the spin j, I didn't write here, so each link is colored by spin j, and each node we're given by intertwiner. So why is this intertwiner is given by exactly this 4-valent node intertwiner? So we have a coupling of 4 spins. A coupling of 4 spins gives you an extra intertwiner label, which is larger than G1 minus G2, smaller than G1 plus G2, and the same thing for G3 and G4. Of course, this is a very special recoupling scheme. You can choose another one. But this is the intertwiner in the spin network states. OK, so this is a boundary graph. So this is only for a single for simplex. In principle, we can have it for very general triangulation of the whole space-time, not only for a single for simplex. Here, I give you a very simple example. This is basically a Dart 3 triangulation. So we have 3 vertex. And so for this graph, the spin-form model is defined as gluing vertices over each edges. And for each edges, we identify and integrating states for the edge. So basically, we have boundary spin network states for each edge, and then we identify them and integrate them out. So in principle, in the current state representation of the boundary spin network states, they have some geometric explanation as tetrahedrons. And this is somehow we summing over all possible. We identifying the tetrahedron and summing them over. And also, we can have internal faces, and we color the internal faces with spin here. So it's representation labels. So this internal face, for example, this one, also need to be summed over. That's define the whole spin-form amplitude on this 2 complex, or the solar decomposition of the space-time. And in general, any spin-form amplitude is given by the following form. We have a phase amplitude, which we call AF. We have edge amplitude, which we call AE. And on each vertex, we have the vertex amplitude. Usually, the vertex amplitude is the most important part. The phase amplitude will only give you some dimension about your representation, boundary representation space. It's the spin. Basically, it's related to the 2j plus 1 somehow to some power. And edge amplitude, it depends the representation. In some representation, we don't have the edge amplitude. So the main thing is the vertex amplitude. I'll tell you later on a concrete formulation for the vertex amplitude in the EPRL model. OK, so basically these are all the basic stuff about the triangulation. I don't know if you have any questions at this level. No? Then we can continue. So now we go to a concrete description of the EPRL model. Before we do that, we need to do some representation theory. So it's 4D space-time, as Francesca already told you. It's SO13, and we go to the double cover, which is SL2C. That's our gauge group. First, we would like to know something about the representation theory of our gauge group. And it's not like what you have learned during the quantum field theory. It's not the quantum field theory. You have the spin-spin representation. It's not a unitary representation. The unitary representation of the SL2C is given by the so-called principal series. What is the principal series? So you see the SL2C have 2 Casimirs. Of course, SL2C generator is given by GI, which is rotation, and KR, which is boost. And it has 2 Casimirs labeled by 2 variables n and rho. So n is a natural number, and rho is a real line. And this, when we write representations, we use Casimirs. So these two labels gives you the label of the representation space, which is the principal series of the unitary irreducible representations of SR2C. So the Hilbert space is given by the rho and n, labeled by rho and n. So this is not the thing we are familiar with. For the thing we are familiar with, this theorem told you that for this irreducible representation space, we have a decomposition into the SU2, because SU2 is the subgroup of SR2C. So of course, we can use the subgroup to label our representations, because its states is, of course, part of the states, mapped to part of the state of the SR2C representation. So this decomposition is given by the following. So it's the sum of all the SU2 representations, and this DJ is SU2 representation. This is what we are familiar with. The JM states, which is given here. So we use J square, which gives you JJ plus 1. This is the eigenstate of J square, and also eigenstate of J3, which gives you the magnetic numbers. And then this is the summing over all possible spins, Summing over all possible spins of the SU2 representation space gives you a decomposition of the rho n space for given rho n label. So this basis is called the canonical basis of SR2C unitary irreducible representations. So for this canonical basis, we use GM to label some certain states, and we also have the rho n label. So in total, we have 4 labels. We have C1, C2 Casimirs, and we have G square and G3. We use these 4 things to label our states. And the metric elements, of course, is given by rho n label and also G1, M1, G2, M2. J can be different because we have summing over J. So this is different into SU2, where the J is the same. We'll derive the matrix elements. And then we have the standard resolution identity, which summing over J and summing over M. So that's the basics of the SR2C unitary irreducible representations. And how the spin form is defined. So this is a very complex thing. We know EPR model, or the spin form model, is basically SR2C BF theory, which is the topological theory, plus the weakly imposed simplicity constraint. So what is BF? BF theory is a topological theory that tells you that all the connections are flat, which basically writing here is a delta function, tells you that all the holonomies, all the loop holonomies are identities. So this is the topological theory because all the connections are flat, basically. So then we have Pitt-Weyl theorem. So we can rewrite this delta function as summing over representations. So this is the next step. So we rewrite this delta with loop holonomies into summing over representations, and tau f is a certain representation on each face. And loop holonomy is around the face. I didn't write here. And then, so we can decompose this trace into the following way, into the following diagram. Usually we call it keyboard diagram. Why is this keyboard diagram? Because we can rewrite this integration of the trace into some integration of the representation matrix with the same D, with the same G. And this is what, if we are familiar, you already learned during the spin network state, this is a projector into the invariant space of the SR2C. So we decompose this trace into the projector into the invariant space. And this is given by the DG. So we have on this 5-edge diagram, we have 5 DJs on each edge. And then it becomes the projector with 4 valence. So it's like this. And so this is the geometric representation which I represent this G with this line, the matrix elements. And you know matrix element has the bra and kit states. So the bra and kit states are labeled by this arrow, which tells you from it's an arrow from source to target. So this is colored edge. It's not the plain edge. So this is the BF. It's not gravity, we know it, because it's a topological field theory. Gravity is not topological. So we need more things to the topological field theory. And these more things, classically we say we need simplicity constraint, which is like second-class constraint. So here, so in this quantum model, we impose it weakly. And it turns out, impose this weakly, it somehow add boundary conditions to the model. And this boundary condition is the following. So here, everything for the BF, everything is SL2C. So all the boundary states is actually a states with SL2C unitary irreducible representations. It's labeled by rho n. But what this weakly imposed simply constraint, usually we call it Y map, tells you that the boundary state is isomorphic to the SU2 representations. So basically, we put boundary conditions to the SL2C Hilbert space. We restrict it to the space that are isomorphic to the SU2 representations. And this is going by the Y map, which maps the SU2 representation into this very special representation of the SL2C, which rho is equal to 2 gamma j, and n is equal to 2j, and we only take the lowest L. If you remember, SL2C Hilbert space is isomorphic to a summing over all possible L, which is larger than n over 2 over the dl. But here, it's only dj is taken, which is the lowest order. And so this gives you so this boundary condition basically imposes the defects which makes this theory not topological. And we call it Y map, and it can be represented in this way. So after Y map, we have the standard BF theory, but for the boundary, we cut it with this Y. And it maps, for the below lines, it maps to the SU2 instead of SR2C, SU2 states. So that's why I use the blue color. So, and then for SU2 boundary state is then mapped back to the SR2C states, and you take the vortex amplitude or the amplitude calculations. This is basically the EPR model. And here I write how this group element acting, the Y map, for the Y map action of the matrix element. So this matrix element is then taken only on the state of SU2. So it's basically given by the percentilda Y, G, so it's Y diagonal, and percent. And this, sorry, percentilda, and percentilda is SU2. And this matrix element is then only given by the same J. So remember, for the SL2C, we have L1, L2, so they can be different. Here, they are the same. The only different thing is the magnetic numbers. It's not the spins. For SL2C representation, the spins, L2, L1, L2 are spins. They can be different. But here, you have the same thing. So that's the SU2. OK. So it still looks like complicated. Yeah.
No, it's silly. Only a silly comment. It's exactly the same notation as everything as Francesca said, except your k is twice the k of Francesca.
Yes, exactly. That's I called n. Yeah, exactly. OK. But this is still very complicated to calculate because we need to calculate basically the SL2C representation matrix is even in the SU2 basis, but it's mapping back to the SL2C representation. It's still really complicated. And how to calculate this is the next task. But before we do that, let's see. For the SU2 boundary, we know the boundary state is spin network states. We have the gauge group SU2, we have the invariant states, which is given by the intertwiners. Sorry, so this is basically a graph for the vortex amplitude, which only labeled by the spin for each phase of the boundary link, and also the intertwiners. So in total, we have 15 numbers. So this is 10 spins, and we have 5 nodes, which has 5 intertwiner labels. Okay, and we know this. This basically we write the intertwiner in this way. So I think Krishna already told you. If you know the SU2 spin networks, you'll understand what happens. And this intertwiner is basically a decomposition of the projector of the SU2 invariance. And you can rewrite the SU2 invariant with these very special 4G symbols with the I, generalized 4G symbols. Yeah. Okay, one important remark is this Y map is only on the boundary. It's not inside. So here we don't have Y map. So it means, here you can write, so this is basically a representation matrix of GT with GS, sorry. GT minus 1 multiply GS. Remember we have arrow, and this is the S, this is T. And for S, we have GS. For T, we have GT. And this arrow tells you this is the GT minus 1 GS in the loop polynomials. So this tells you that the Y map is only on the boundary, so in between. If we want to write them separately, we need to insert the resolutional identity. And this resolutional identity is not SU2, is not after Y map, it's the full resolution identity of the SR2C representation matrix. It means we have 2 labels for this. If we want to write the resolution identity, we have 2 labels. One is M, another is M. And L must be larger or equal than all the spins, which given by the boundary graph. Okay. So with this, somehow we have enough information to derive a much simpler description of the spin-form models, which is called Bolster decomposition. And this can also be done graphically in the following way. So we have the Cartan decomposition of SR2C. I think you may already know this. So each SR2C group element can be written with two different SU2 group elements, multiply boost. And the boost is only on the third direction, is only on the K3 direction. So with this, we decompose somehow the representation of the SR2C into representation of SU2, multiply representation of the boost, then multiply another SU2. So graphically, I write something like this, sorry. So we have SU2, SU2, and we have boost in between. And we know on the left, we have the Y map and the intertwiners is SU2 invariant. So this SU2 group element acting on the SU2 invariant is trivial. We can just ignore it. So we get this. And for the right-hand side is SU2. Remember, we have the SU2 decomposition of the representation theory. So we have sum L larger or equal than J, dj. And this SU2 introduces the projection onto the invariant space of SU2 for each L. So we have a summing L and summing over intertwiners in between, and it becomes the SU2 invariant, which is the intertwiner. It's again, for one of the intertwiner, the difference is now we have different L. So this is a decomposition of the SU2 representation matrix, SR2C representation matrix into SU2. And you can calculate this part up to here, which is a B matrix, is a B matrix labeled by GF on the left, which is the spin we have on the boundary states. LF, I just write, is larger or equal than J. So LF is larger or equal than GF from the decomposition of SR2C. And then it has also, on the left, the interternal label of our boundary state. On the right, the interternal label of our decomposition. So in this decomposition, L, F, and K need to be summed. So we will talk about it later. The good thing is now we only have one variable. So SL2C have 6 variables. That's the SL2C group, you know. But now we reduce this group into an integration with one variable. Then simplify a lot the calculation, and this is called a booster function. More things. Now we decompose the vertex graph we had in the previous slides. So this is basically tells you the vertex amplitude of the spin-form model. Now using this decomposition, I write it in this way now. So here I have KE, here I have KE prime, and all the third ones, they are similar things. And now you see the intermediate graph, they closed. And they closed with SU2 labels. This is what? This is the 15J symbol, if you are familiar with BF theory. And why is 15J symbol? As I said, we have 10 spins. Sorry, it's L. Sorry, 10L and 5 KE. So that's form the 15J symbols. These are the 15 numbers, basically. And then we multiply the booster function. Outside, the booster function is a function of the boundary spins and the internals, and also the spin and the internal for the 15J symbol. And finally, the spin of the 15J symbol and also the internal for the 15J symbol need to be summed over because it's coming from our decomposition. So they need to be summing over. That gives you a decomposition of spin form amplitude, which is the boundary, a function of the boundary labels, into a summing over of the spins and the intertwiners of the decomposition with a booster function, which is SL2C representation. If we don't have this SL2C representation, it's exactly the SU2BF amplitude. So what spin form tells you is the actual thing, which called booster function, encode the SL2C information into the SU2 topological theory. So this basically gives you an ansatz to calculate the spin form amplitude. And this is the basics of the SL2C form next package. One tricky thing is here. In principle, you see LF is larger than GF. So you need to sum over everything into infinity. But numerically, we cannot sum it over into infinity. So we need to introduce some cutoffs. That's an approximation. So basically, in numerics, we approximate it with some cutoff, which cut off the L, the intermediate sum you can have. Of course, it's an approximation, so I need to check if it's really converge. Okay, so here we finish this booster decomposition. I don't know if you have any questions. It's a bit technical, but basically, all the decomposition, you can find all the details in this paper by Simoni, which written Simoni Spazio, which write everything clearly in the booster functions. And you can find the detailed form of this booster function, which is the representation theory of the small d Wigner matrix. Yeah.
So I was thinking about if you, so is it known that this will converge to some finite number if you would sum all the way to infinity?
It's converged because you can think in this way. So the large spins, for small spin representations, for the J small, the large L does not, they contribute very tiny. So they peaked on the small spin part. So that's why they converge.
So it's also justified to cut off because it will converge?
Yeah.
Okay.
Yeah. Of course, this also tells you that when the spins becoming large, it's more and more hard to calculate everything because L need to be large and all the intertwiner space becoming larger and larger. Yeah. Any other questions? if no, we can move to another part. So as said, so this is both the decomposition. Is one representation of the spin from vortex amplitude. We have another representation. As I said, this is for small spin, deep quantum regime. If spins become large, it's harder and harder to calculate. But for large spin, we have the asymptotics. And asymptotics is somehow related to the semi-classical property of the model, so we use coherent states. Thanks. Yes?
So for this spin G is large, so this boost function is peaked at this large G, or?
That I'm not completely sure, but all the large G must contribute, large L contribute. That's the thing.
So my point is like you introduce some cutoff for if this spin G is small.
Yeah,
But
large G also you introduce cutoff, but it must
yeah,
be.
but my point is like if this G have some peakness property. So for instance, if the GF is fixed and consider this B as a function of this L, and
Yeah.
if it is like a Gaussian package, and then we can just sum over those spin L around this G rather than from.
It has some peakness because the boost function contains the 4NG symbols. So it contains both L, the J and L 4NG symbol. So somehow it has a certain peakness, but it may not be a Gaussian.
Yes, so if it is like have this peakness property, that means like we only need to consider this L around this large.
No, you need to around, but you don't know at least I don't have any estimation of how large it should be around. The distance.
So you mean the spread?
Yeah, the spread, we don't know. So at least we need to do it sufficiently large such that the amplitude does not change when we change L, when we change the cutoff. That's a good estimation. Yeah. Any other questions?
What is your intuition about this being a tetrahedron actually boosted?
Sorry?
What is your intuition about this booster thing being a tetrahedron just for every R boosted by R to another tetrahedron? Can you see this? Sort of the data of a tetrahedron on the right, data on the left, and the boost between the two. Can you see something like that? Or do you think in these terms?
I think it's related to that, but I don't know any concrete things.
Just a question. You know.
Yeah, but it's
I don't have clear ideas.
yeah, it's a boost about the tetrahedron on the left, and then contracted with the tetrahedron on the right. Basically, it compares the boost of one tetrahedron with another. Basically,
It's parallel transport.
yeah,
Right? It's a parallel transport of the normals of the tetrahedron.
Yeah.
So that's what you think about it. It's really parallel transport with boost.
Yes.
Yeah.
Yes.
Yeah.
I was thinking this way.
It's parallel transport the left tetrahedron and then compare into the reference frame of the right and then compare with it. Yeah, of course, this both is only on the third direction. It's not rotated. Yeah. So I guess we can continue. Yeah.
I have a sort of naive question. So when you introduce the resolution of identity there, it's in the SU2, right?
No, it's in SL2C. That's why I said there is the summing over L. That's a resolution identity in SL2C. If you check, this is the resolution identity in SL2C.
Uh-huh.
That's why we have a summing over. Here I call it J, but later on it's L.
Ah, okay.
So there is summing over spins. It's all the resolution identity of each spin, SU2 representation.
So this 15J symbol you get is then defined in terms of spins in the SL2C.
It spins of SU2 because we have the decomposition of SL2C representation into a summing over all SU2 representations with spins summing to infinity. That's why we decompose it using SU2. But it's not fixed spins SU2. It's spins up to infinity. That's why we have this summing over things.
Thank you.
Yeah, okay. So then let's move on. We go to the integral representation. Again, we start with SL2C representation theory again. So previously, we write the states as rho n, Gm. This is one way to write out. It's a basis of our Hilbert space. But we have another way to write out to write out the Hilbert space. The Hilbert space actually, if you learn about the representation theory, is given by the homogeneous functions. Homogeneous functions of spinors, and this Z is a spinor. So what is the homogeneous function, first of all? Homogeneous function means it has some homogeneity property, and this is the homogeneity property. So you see, when we scale Z, alpha is a complex number. So when we scale that, it behaves like this. So alpha with 2 representation labels and alpha star with 2 representation labels. The only difference is this is plus for n and this is minus for n. So the SL2C unitary irreducible representation is realized on this space of homogeneous functions in the following way. First, we have action of the SL2C group element is just action on these homogeneous functions becoming action on the spinors with the transportation of the group elements. And then we have the scalar product of the Hilbert space, which is given by the standard complex conjugation and with a very special measure. And why we chose this special measure is such that the whole thing is invariant under the action of the SL2C group. And also it's invariant under the scaling of the spinor, which somehow we project this integration into CP1, and this is the measure, exactly the form of the measure. So this forms, with this scalar product and with the action, this forms a representation space of SL2C group elements. And of course, we define the Hilbert space. This is exactly the previous Hilbert space defined on the states that the scalar product is not divergent. So with these homogeneous functions, we can realize all the, we can write explicitly what happens for the inner product using the integral, you see here. That's why we use this. Now we move to the decomposition. So as we said, H rho n, how do I change the color, sorry. H rho n is somehow decomposed as the summing over J larger than n half dj. So we use, again, SU2 states to write out the Hilbert space. And now this embedding of SU2 states is realized in this way. So this is the homogeneous function, and it's given by ZZ, which is spinner's inner product. And this is SU2 invariant inner product. It's a standard one, which is the Z plus, Z bar, Z plus Z minus, Z bar, Z minus. So this is a standard scalar product of the SU2 invariants. Spinors, sorry. And this per se GM, Z is a function of the SU2 Wignard matrix. And you can check this satisfies the homogeneous property, which is very easy to check. And this embedding of the spinors into the SU2 group element is given by this. And then you can write everything using the Wignard matrix of the SU2. And you have an explicit embedding of the SU2 representation matrix with the states of the SL2C Hilbert space. And of course, here G can be different because we have j larger or equal than half of n. And Y map fixes the j exactly. So we only have k equal to j for Y map. And this means we have a very concrete formula for any states on the Y map. So for a state of SU2, we have this percent, and we map them, into the SL2C state with this formula. That's the embedding. So this embedding now is explicit in these homogeneous functions. One more thing is, as I said, this is still using the spin and magnetic numbers, but we would like to transform to coherent state to avoid the magnetic number, because magnetic number is still sum. We would like to have an integral formulation, which is not sum, but integration. And also we have some semi-classical properties or geometric meanings of this thing, and this is introduced by SU2 coherent states. So what is SU2 coherent state is defined in the following way. So we replace the magnetic number with a spinor. This cosine is again a spinor. And we know any spinor is corresponding to SU2 group element or this way. So this is also a SU2 group element acting on the highest weight state of SU2. Highest weight state is the JJ states, which M, the magnetic number, equal to J. And from this state, we rotate this state, we get all the coherent state of the SU2 group elements. And we can write out explicitly what is this highest weight states, because if you are familiar with SU2 representation theory, the Wegener D matrix, the highest weight state here is nothing else but the one-half states of the SU2. Basically, is the fundamental representation of the one-half with the 2J power. This is a very simple formulation. And then you can write them using this formulation we use it in terms of spinors. And it turns out it's a very simple formulation, which I also introduced N plus, a very special spinor, which is 1, 0. And this spinor is nothing else, tells you that this is corresponding to a z-axis of a normal along z-axis. And then, with the definition of the coherent state, we write out the SU2 coherent state, which is now we know what is the action onto these homogeneous functions is just Vt multiplied z. And this z transforms to cosine. And this cosine is exactly the transformation of the group element, which is SU2 multiply this spinor. And this corresponding to you use SU2 group elements to rotate the normal along the z-axis or the E3 axis into other directions. And this is the geometric meaning. So basically, this cosine tells you it's a normal. This is 2D version, but if we go to the spin 1, it's corresponding to a 3D normal, which is exactly the rotation of the SU2 multiply 0, 0, 1 of the basic highest weight states. The highest weight states is picked under the J3 direction, if you want. Yeah, so this is SU2 coherent state, and then we can embed it into the original SL2C representation states, which gives you the SU2 coherent rate SL2C states somehow using the Y map. And with this, we can write out our vortex amplitude. And you can follow all the calculations. So this is the standard thing we have also for the BF theory. Now what we have exactly is this part. I write it now using the coherent state, which we have labels J, and we have the labels cosine, which is the spinors, which tells you the direction of the normals of the triangle. And then it's a very simple calculation. You can follow all the steps if you insert the detailed form of this process and how the SL2C group element acting on these states. Finally, you get a compact formulation, which is this one. So we see we have something which has which is the power in terms of GF, and we rewrite this part as the action, and we rewrite the remaining part, which is this part, as the measure. So in this way, we obtain an integral formulation, which is the measure multiply the action, exponential of the action. And the action is defined by the logarithm of this part. And you'll see the action is linear in the spins. That's one important property why we say the large spin is asymptotic, because the action is linear in spin. And we have the theta point approximation exactly tells you when the spin is large, we have the theta points dominant. This is a very special formulation. I mean, it's not so complicated, but this is what we obtained from the representation matrix. And if you have time, you can do this calculation very easily after you go back to your hotel, if you're interested. Yeah, so this is the thing. One more thing I want to set. So this is the vortex amplitude. We fix our boundary, and the boundary is fixed by the Coset, which is the normal of the triangles. Normals of triangles of the tetrahedron, or boundary tetrahedron. And spin is the area, more or less the area, as Francesca already told you. Area of the triangles of the boundary tetrahedron. So we have this, so this gives you all the boundary data, which is the geometric data of the boundary. And then from this geometric data, we obtain the spin form amplitude. One more thing I want to say is we can go beyond the single vortex, as I said, by gluing the boundary tetrahedrons. And now the gluing of boundary tetrahedrons introduce, of course, the integration over the boundary Cosets, which is the geometric data of the boundary tetrahedron, and also the summing over of the internal spins for the internal faces. One more thing is this must be a formal tetrahedron, so there is a closure condition, which basically projects you to the interternal space if you want. Okay, that's all. There's one more thing is about gauge transformations. Because now we have an action, we can talk explicitly what is the gauge transformation, which is leaves the action invariant. So for the vortex amplitude, we have that, if you still remember, is defined as GT multiply the small z, which is defined on VF. This is capital Z. We have the following gauge transformations which leaves the action invariant. The first one is a discrete one. We can add plus or minus sign to each group elements. And there are 4 continuous gauge transformations. And at each vertex, we can multiply an extra group elements. And for each CF, we have the free scaling, which is corresponding to the CP1 we discussed before. And for each internal edge, this is only for the internal one, we have the gauge transformation, which we can multiply a face to our spinors, which makes only, so spinor has 4 degrees freedom. And because of this face, we only have 3 degrees freedom. And also, actually, it maps into 2 degrees freedom, which is only the normal direction. And the fourth one is that we have a gauge transformation with SU2. So HE is SU2 for the internal spinors. And this is relevant for the projection into the internal space, if you want. Yeah, with this, I think I can close. So these are all the formulas I want to discuss. And I don't know if you have any questions. Yeah, if no, I think it's a break.